In the last lecture, we have left with our swing equation, that was our m d square delta upon dt square is equal to ps minus pe. Okay. Now here, if you see the quantity, m was j omega, right? So we have replaced m with j omega and we have find out this relation. Now this m, it is not always constant. Okay, not always a constant quantity. Okay, and here this swing equation majorly comes in picture when there is a change in power change in power. That means under transient conditions, okay. So whatever omega what you are using here does not seems to be in to be a synchronous speed. Okay, so that's the big problem. uh, Here m is not constant because the swing equation applies for when there is a change, when there is an acceleration or when there is a deceleration. Okay, and when there is an acceleration or deceleration, that means the speed changes, right? And if your speed changes, that means m will not be in constant position. And one more problem maths suggests that it's better to it's not a problem, but it's in electrical or in mechanical engineering, it's better to better to measure power power than torque. Okay, it's better to measure power than torque. So for this power measurement, we want any quantity that has a power unit here. Okay, so that's why we developed one more quantity, that is h. H is, I'll tell you the advantage here. Now h is the ratio of stored kinetic energy in MVA, in megajoule at synchronous speed. Okay, and upon rating of a machine. Okay, in MVA. Now what I can say here, stored kinetic energy, by the definition in mechanical terms, you can say half j omega square upon s. Okay, now so what I can say here, if half j omega square, I am partitioning it like this, omega into omega and divided by s. So what I will write, j omega, I can put m, so I will write m omega upon 2s. Okay, for h, this is our h. Okay, then how can I write? H is m omega by 2s, so m can be written as 2sh upon omega. Okay, now I will put it in my swing equation. Swing equation was m d square by dt upon dt square is equal to p s up minus pe. So I'll put it here, so I can write 2sh upon omega d square delta upon dt square is equal to PS minus PE. Now I'll just reshuffle some terms here. If I reshuffle HS to this side, what I can write? I'll write PS upon S minus PE upon S, right? So now this S is the rating of my machine in MVA. Okay, in MVA. So this is my in terms of MVA, if it is the highest rating or rating of the machine that a machine is been rated. Okay, so if you check it in this equation, it is nothing but per unit value, per unit value, per unit value in powers. Okay, in powers. So this is the per unit side, right? So and you know the advantage of per unit. Per unit means actual quantity. Actual quantity is PS, and the maximum quantity, that is S, that is the base value. So actual quantity is PS and the base value is S. So actual quantity is PE and the base value is this. So this quantity, this equation has converted into a per unit power equation. Okay, now one more thing here is that if I use del m, this subscript m will tell us that I am calculating angle in radian in mechanical units. In mechanical units, okay, mechanical unit. I have already discussed this in the last class. So if I am using del m in mechanical unit, I will put m. If I am using del, I am using angle in radian in electrical. Okay, so there are two different terms, just remember. Now if I am using del m, I will use omega sm. Okay, what is S? Synchronous speed in mechanical unit. Okay, and if I am using del, I'll use omega s. Okay, so if I change the equation in mechanical side, this differential equation, 2h upon omega sm del d del square m upon dt square is equal to ps upon s minus pe upon s. So here I am using the swing equation in mechanical side. Okay, and if I want to replace, I want to use swing equation in our electrical side, so I'll replace this with d square del upon dt square is equal to ps minus pe upon s. Okay, so this is the difference, that you can use both equation on both the sides, either in the mechanical side or in the electrical side. Now what has changed? What has changed here? If you check here, I have started this with some assumption. Sorry, what I have changed here. So this is our equation m d delta square upon dt square, right? Now here I have already told you that m does not seems to be in constant, because there will, this swing equation changes with respect to your acceleration and the acceleration. When the instability comes, then only the swing equation comes in picture, right? So here this equation has changed to this omega s d square delta upon dt square ps minus pe upon s. Okay, now this unit, if you change it, I have told you that it's better to measure power. What is the h unit? H unit will be megajoule per MVA, right? So power unit is joule. So it's better to use power unit. That's why I have used this parameter H. Okay, and this m was your actually a momentum, angular momentum. So that's what I have changed here. So this quantity now with respect to the per unit quantity will remain consistent. Okay, will remain consistent. Okay, and now it is operating at your synchronous speed. So that's why you can write this equation 2h upon omega s. If you write, you can write it as 2 pi f, right, d square del upon dt square ps upon s minus pe upon s. Now you can cut this, so you will remain with h upon pi f. Now you can replace pi with, if it is in a degree, so you can replace this equation is in radian. So if you want to use this equation in degree, so you can replace 180 with pi f d square del upon dt square ps upon s minus pe upon s. Okay, so that's why this equation has been now can be applicable for any situations when the power changes. If the power does not change, that means the acceleration is zero, and now this quantity is constant. But therefore the problem was removed. Okay, what was the issues? That now the equation remains with h upon pi f d square delta upon dt square is equal to ps minus pe, and this is in per unit quantity. Okay, so that's why I'm not writing upon s. Okay, now what happens now, if you check here, this I have already told you that this is our acceleration quantity. I can change this quantity with respect to your d square. If I want to change this in terms of omega, so I can write d omega. Okay, d omega by dt, right? Now here, what was the difference? What delta and omega was d square d delta by dt, right? And alpha was d square delta by dt, and that was d omega by dt, right? So I'm replacing d square delta with d omega by dt, and I can write pi f. Okay, so this is ps minus pe. So this is equation number 1, and the next equation which you can change here is that d delta upon dt is equal to omega, but this omega is actually a change of velocity. Change of velocity means omega minus omega s, change with respect to your synchronous speed. Because this I have told you that this equation will comes when only this power changes, means there is a difference between a mechanical input and electrical output. And if the there is a power changes, that has an effect on your speed change. So that's why there has to be a speed change, then only this equation will come in picture. Now what I have done here is that I have separate, if I want to use one if I want to use one swing equation, I have separated the swing equation in two simple uh, first order differential equation. This was our second order differential equation. This swing equation, I have broken this swing equation in two single order differential equation. Okay, That's what the advantage in this equation is.